Hello from Chem Help ASAP. Why are activity curves so often sigmoidal in shape? Let's see why this is typically true. Here we have two sets of axes. One is the effect of a ligand versus ligand concentration. The other, on the right, is the effect of a ligand versus logarithm of ligand concentration. The curve on the left normally looks like this. As ligand concentration rises, the effect of the ligand initially very quickly rises. Continued increases to ligand concentration slowly raise the effect to an eventual plateau. You might have seen this type of curve, a rectangular hyperbola, in enzyme kinetics discussions. The ligand is a substrate, and the effect is the rate of the reaction, which approaches Vmax. If we switch to a log ligand concentration on the x-axis, then our rectangular hyperbola becomes a sigmoidal curve. Again, we can approach a maximal effect. The curve on the right is how the activity of drugs is often presented. Just keep in mind, if you are looking at a sigmoidal relationship, it is just about a guarantee that the x-axis is logarithmic. This sigmoidal relationship arises from something called occupancy theory. In occupancy theory, the magnitude of the effect is directly proportional to the occupancy of the target by the ligand. That is, the percentage of target bound by the ligand. 0% target occupancy will give 0% effect. 50% occupancy gives 50% effect, etc. The relationship between occupancy and effect is linear. This model is often called Clark's occupancy theory, and it is based on the dissociation equilibrium between the ligand binding or drug binding and the target. This model is not perfect, but it often works well for many targets. Let's see some mock data. Here is a table of ligand concentrations and E over Emax. Emax is the maximal effect. E over Emax is equivalent to the receptor occupancy, based on occupancy theory. To the lower right is an equation that represents the relationship between E over Emax, which is the y-axis value, and ligand concentration, which determines our x-axis as log ligand concentration. We need to know Kd for this discussion. Let's assume that we've experimentally measured Kd as 10 nanomolar. To achieve 10% of Emax, E over Emax is 0.10, we would need a ligand concentration of 1.1 nanomolar. You might expect that boosting E over Emax to 0.20 would require doubling the ligand concentration to 2.2 nanomolar. No, ligand concentration needs to more than double, from 1.1 to 2.5 nanomolar. What if we want to double E over Emax again to 0.4? Concentration again needs to more than double, from 2.5 to 6.7 nanomolar. Let's double the y-axis again, up to 0.8. Concentration has to way more than double, from 6.7 to 40 nanomolar. That's about a six-fold increase in ligand concentration to double the response level. So while occupancy and effect follow a linear relationship, the ligand concentration and effect do not share the same linear relationship. Over time, researchers have found the most convenient way to visualize the relationship between effect and ligand concentration is as log of ligand concentration. In this depiction, the trend generally appears as a sigmoidal relationship with the point of inflection occurring at 50% Emax. That was a quick introduction to the idea of occupancy theory and explaining why we see sigmoidal activity curves. I hope you enjoyed the video. Please like, subscribe, or leave a comment. Take care.